Good morning, Panthers. It is Dr. Augustine, and today I am going to work on an example problem related to precipitation reactions. This is actually sort of a part 3 video on aqueous precipitation reactions. The first part was describing the solubility rules, how to use them to predict when a precipitate is going to form. The second example was how to write out molecular, complete ionic, and net ionic equations. And today we're going to do an example of doing both of those things and also doing a stoichiometry problem related to it. So here's the problem. We have a solution, beaker A, beaker B. Both of them are dissolved ions, and let's just pretend there's actually more space between them. Just for the sake of argument, they're drawn close together, but there really would be a lot more space with water molecules in between them. And so the first question is, part A, which compound is dissolved in beaker A? We got 4 different possibilities here. And the way to attack this problem is to look at what the species actually are that's in the solution. So we've got a +1 ion and we've got a -2 ion. So if we look at our examples here, sodium phosphate, sodium would be a +1, phosphate would be a -3, so it can't be that one. Calcium chloride, calcium is a +2, chloride's a -1, it cannot be that one. Magnesium sulfate, magnesium is a +2, sulfate is a -2, so therefore the answer must be sodium sulfide, Na2S, and it's an aqueous solution. Okay, likewise, problem 2, and by the way, you can stop the video and answer this yourself. So problem 2, which compound is dissolved in beaker B? I'll change the pen color just so we're talking about beaker B here. We've got a +2 ion and a -1 ion. And I've got a couple different possibilities here. I got barium sulfate. Barium's +2, that's a possibility. Sulfate is also a +2, so it can't be that one. Cadmium nitrate. I'm not sure what cadmium is. It's a transition metal. But we know a nitrate is -1, so that's possible. And the 2 has come down here, so that means cadmium nitrate's probably the right answer. Let's just keep going and check. Aluminum chloride, aluminum's always +3, chloride's always -1, so that's not it. Potassium's always +1, carbonate's -2, so cadmium nitrate is my other species. So let's write that down, CdNO3, 2, aqueous. Okay, so let's look back at the problem now, and we notice the next problem, part C, name the precipitate and spectator ions when solutions A and B are mixed. Write the balanced molecular, complete ionic, and net ionic equations for the reaction. So there's a couple of steps here. It's actually probably easiest to name the precipitate and spectator ions once you've written the molecular equation. So let's take a stab at the molecular equation. So if you recall, here's my reaction, and I'm going to write an arrow. And you might remember that we take the cation from one species and react with the anion from the other species, and then we take the cation from the second and react with the anion from the first. It's called an exchange reaction, and that's how we're going to try to figure out what products are formed. So let me just erase these, and we'll do that. So we're going to say sodium nitrate. Sodium is a +1 ion, nitrate's a -1 ion, so they're going to cancel. And using the solubility rules, we know that sodium is a group 1 cation, always soluble. Nitrates are also always soluble. So we can use that fact to figure this out. And then we're going to do an exchange reaction. So we're going to take the cadmium ion, which is a 2+ ion, and the sulfate ion, which is a 2- ion. We're going to react them together. And so they're going to cross, those charges are going to cross down and they're going to disappear. And this is also not going to be aqueous. This is going to be a solid. And you might be saying, well, your table that you gave me, the simplified one, doesn't have sulfides on it. Yeah, but we know this is a precipitation reaction. And we know that both sodium ions and nitrate ions are always soluble. So therefore, this one has to be the precipitate. If we're told it's a precipitation reaction, we can actually use that table without even necessarily knowing what all the different exceptions are. Okay, now taking a quick look at this reaction, you might note to yourself that it's not quite balanced yet. You notice that there are 2 nitrates here, 2 sodiums here, and only 1 on this side. So we need to balance this with a 2. And if we just check the other guys, cadmium 1, 1 cadmium, sulfide 1, 1 sulfide over here, 2 nitrates, 2 nitrates, 2 sodiums, 2 sodiums. Now we have a balanced equation. We refer to this as the molecular equation. Okay, so that is balanced molecular. We've completed that. Now we need to, and we've also identified the precipitate, which is cadmium sulfide. So now let's take a look at complete ionic, net ionic, and the spectator ions. And if you recall how to do this, we need to break this guy up into all its constituent ions to write that complete ionic equation. By the way, some books just call this the ionic equation. Tro calls it the complete ionic equation. So this 2 we need to bring out front because there's actually 2 sodium ions, so 2 Na+, that's aqueous. So remember, whenever you see a little AQ, it actually means it's broken up into its ions. Sulfide 2-, aqueous plus, this one has an aqueous, we need to break this up. Cadmium 2+, aqueous plus, this 2 gets brought in front. There's 2 nitrates, 2 NO3-. These are common mistakes for students to make. And that forms 2 sodium ions, 2 Na+, aqueous, plus 2 nitrate ions. The one in front carries through to both species, another common mistake for students to make, plus cadmium sulfide. And remember, that's a solid, so we do not break the solid apart. All right, so now taking a look back at this, we have, this is broken up into 2 sodium ions. This is 1 sulfide ion. There's no subscript here, and there's nothing out front here, so there's only 1 sulfide ion. 1 cadmium ion, 2 nitrate ions, 2 sodium ions. That 2 carries through, 2 nitrate ions, and 1 cadmium sulfide. That is the balanced, complete ionic equation. Again, some books will just call this the ionic equation. And that shows where the ions are in solution. Now, if we take a look at this, we notice, remember this arrow here is like an equal sign in math, and we have some things on the exact same, on the same side or on the opposite sides. They're exactly the same. So sodium 2+ is exactly the same, and 2 nitrates on this side, exactly the same. So those are the spectator ions. So spectator ions are Na+, and NO3-. All right, so in my problem, we're identifying spectator ions. It's a sodium plus ion and the nitrate anion. And then to write our final equation, we take this once we've crossed out the spectator ions and we just write what's left. And you don't have to do it this way, but kind of by convention, we put the cation first. So we're going to say cadmium aqueous plus sulfide aqueous yields cadmium 2 sulfide, and that's a solid. And this is referred to as the net ionic equation. Okay, this might be a 10-point problem on an exam. This part C here is a sort of a classic example. Write down the balanced molecular, complete ionic, net ionic equations, identify the precipitate and the spectator ions. So if you can do that, that's probably 10 points on your next exam. All right, let's go to part D, and this is really a stoichiometry problem. So let's take a look at part D and see how this is worded. If each particle represents 0.01 moles of ions, what is the maximum mass in grams of precipitate that can form, assuming a complete reaction? So if you look at this carefully, you notice, first of all, you're going to have to do some counting here to figure out how many moles we have. But second of all, it's asking for maximum mass. What's that another word for? That's another word for the theoretical yield. So we're trying to find the theoretical yield of cadmium sulfide that's able to be formed. And we also don't know which one's going to run out first. So we have to assume this is actually a limiting reagent problem. Whenever you're not told something is in excess, we have to assume it is a limiting reagent problem. All right, so the very first thing we need to do is I'm just going to write down what information we have. We have beaker A, and we know it is sodium sulfide. And we have beaker B, which we know is cadmium nitrate. Okay, and we also know that each one of these particles, each one of these circles represents 0.01 moles of ions. So we're going to need to do a little bit of counting here, and probably the easiest way to do this is to count the one that is the least in here. So in this case, there are less sulfide ions than there are sodium ions. There's twice as many sodium ions as sulfide. So it's probably going to be easier to count the sulfide ions. So we'll just go around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 S2 minus ions, which means there must be 28 Na plus ions in beaker A. And in beaker B, there are less cadmium ions than there are sulfide ions. We'll count those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 cadmium ions, and there must be 24 nitrate ions. And you can count them to convince yourself if that's true. So if that is the case, that means we've got, we'll take beaker A, for example. We have 14 sulfide ions times 0.010 moles of sulfide ions per picture on there, which means we have 0.140 moles of sulfide ion present. Likewise, in beaker B, we have 12 cadmium ions times 0.010 moles cadmium. So that's going to be equal to 0.120 moles of cadmium, 2 plus. This should be 2 minus, sorry. Okay, so those are our concentrations. Again, we could double these concentrations. That would give us the sodium ions and the nitrate ion concentrations. Now, looking at our balanced equation, you notice these are in a 1-to-1 ratio, 1 mole sodium sulfide per 1 mole cadmium nitrate. Therefore, the cadmium has to be the limiting reagent because we have less numbers of moles of cadmium. Technically, we might have to do a calculation. If they're not in a 1-to-1 ratio, you may not be able to see that right away. But in this problem, we can see there's less cadmium. They're in a 1-to-1 ratio, so this has to be the correct one. All right, let's just finish off this problem then. We'll do it to completion. So we have 0.120 moles of cadmium 2 plus, and technically we need one more little calculation here. We need to have 1 mole cadmium nitrate, NO3, 2 for every 1 mole of cadmium ions. Again, this happens to be in a 1-to-1 ratio. They're not always going to be in a 1-to-1 ratio. Now we're going to say 1 mole cadmium sulfide for every 1 mole of cadmium nitrate. Again, they happen to be in a 1-to-1 ratio. That's not necessarily generally going to be true. So you can't forget these steps because chemistry professors usually give you problems where you can't get away with forgetting this step, for instance, or forgetting this step, because they'll pick a problem that you have to know how to do these steps in order to get the final answer. All right, and we have one more step. It's actually asking for the mass in grams, so I need the molar mass of this, which I've already calculated, 144.5 grams cadmium sulfide for every 1 mole of cadmium sulfide. So that's going to cancel that, and that is going to equal to 17.3 grams cadmium sulfide. A quick look back at the problem to make sure we have the right number of sig figs, and we see, well, this one only has 2 significant figures, so my answer should only have 2 significant figures. So I am going to change this to the right number of significant figures, so 17 grams cadmium sulfide is my theoretical yield, maximum amount that I can form. You can stop the video and convince yourself that if we use the other one, if we use the sulfide from the sodium sulfide, we would end up with more, so that we can't have more than we actually started with. This is indeed the theoretical yield. Okay, so here's a good wrap-up of precipitation reactions. We've done 3 different types of, 3 different steps we've looked at. The first step is just understanding what a precipitation reaction is. It's actually an exchange reaction. That was in the first video. We also looked at the solubility rules to help us predict which product was going to, in fact, precipitate. The second video was showing us how to do this business right here, the molecular equation, the complete ionic equation, and the net ionic equation, which we've repeated right here. And the third is kind of putting all the pieces together, including a stoichiometry reaction using precipitation as our example type problem.